So I promised you at the beginning of this section that one of the things we'd look at is what exactly it means to say that a matrix is invertible. So this next theorem is referred to as the invertible matrix theorem. Some books will call it the fundamental theorem of invertible matrices. I've known some colleagues that like to call it the monster theorem, not because it's scary or that it's mean in any way, but just that as you progress through the linear algebra course, quite often you'll start with a list of statements such as the one you see here, and the list, as you progress through the course, you keep adding statements to the list. You keep adding points of view, and your perspective keeps growing, kind of like a monster in a story. The monster keeps growing, right? So it's just a bit of a running joke. But let's go through these statements, okay? And you can see that most of them are incomplete. There's something that's left to be filled in. But this is one of those statements that says the following statements are equivalent for an n by n matrix A. And I've written the matrix A as a row of columns here. So the idea is that A1, A2, all the way up to AN, those are all n-dimensional vectors that form the columns of the matrix A. And it's going to turn out to be useful with a couple of these statements because we want to refer to the columns specifically. But let's go through the statements one by one. The first thing you can say about the matrix A is that it is invertible. Now that statement might not always be true. Depends on the matrix A, right? When you read theorems like this, the following statements are equivalent or the following are equivalent. You'll see lots of mathematical theorems worded that way. Remember, I want to remind you what that means. You're saying that all of these statements, they're either all true or they're all false, which is a really powerful thing to observe. That means if you can show that one of these statements is false, that means every other statement in the list is also false. And if you can show that one of the statements is true, that means every other statement in the list is also true. And some of them might be easier to prove either true or false than others. So that's where the power behind these theorems comes from. So yeah, the matrix A might be invertible or it might be not invertible. But if it is invertible, then statement A is true. That means all the other statements are true as well. But if your matrix A is not invertible, that means statement A is false, and that means all the other statements are false as well. So that's how you should interpret this theorem. Okay, so part B, the reduced row echelon form of the matrix A is what? Well, one of the things we've already seen is that if you take the reduced row echelon form of an invertible matrix, this is what the whole inversion algorithm is based on, you better be able to turn it into the identity. And if you can turn the matrix A into the identity, well, then that's what its reduced row echelon form is. So it's the n by n identity. That's the reduced row echelon form of A. Okay. Statement number C, it talks about how many pivot columns A has. And this, by the way, this is equivalent to saying how many pivot positions the matrix A has, or how many pivot rows the matrix A has. Any of those words could have been interchanged with positions, or rows could have been interchanged with columns, and this would still work, but we're going to phrase it in terms of columns. Turns out A has n pivot columns. In other words, every single one of these columns is a pivot column. Remember what that means? It means when you reduce it to reduce row echelon form, or even row echelon form, it tells you how many leading entries you have. It tells you which of your columns are going to have leading entries. That's what a pivot column is. So A better have n of them. In other words, every column is a pivot column. Okay. The associated homogeneous system to the matrix A. Every matrix has an associated homogeneous system. Just treat it as the coefficient matrix of a homogeneous system. That system, if A is invertible, that system is guaranteed to have only one solution. And if you know it only has one solution, you know which one it is, right? Because a homogeneous system always has the trivial solution, which I'll just write in this fashion. But it turns out if A is an invertible matrix, then, well, that trivial solution is going to be the only solution. Remember, this is just a shorthand way of saying, since x is actually a variable vector in this context, the only way this makes sense is that this must be the zero vector, which means this is not setting one variable equal to 0. This is you're setting all of your variables equal to 0. That's why this is the short way to write the trivial solution. Okay, the next statement says that that's not just true for the associated homogeneous system, but any linear system for which A is the coefficient matrix. They all have a unique solution, and that unique solution is given by x is equal to A inverse B. And you can get this just by applying the trick that we outlined in the previous section. So notice that statement E is just a more general version of statement D. In the specific case where B happens to be the zero vector, that means this would be the zero vector. And when you perform this product, you'd actually just get the zero vector again. And then you would end up just having everything reduced down to this statement. But back to reminding you, how do you interpret this theorem? Remember, if one of these statements is true, they're all true. So what if you wanted to prove that this was true? You wanted to prove that for any constant column B, the matrix equation AX equals B has a unique solution. That involves making a broad argument that applies to any constant column B. Well, this theorem says it's enough to just prove that the associated homogeneous system has only the trivial solution. And if you can do that, then you can automatically conclude that statement E is true. So that's an example of how you might apply this. You can show a more general statement by proving a more specific statement, which is easier to prove. Okay, statement F. What do we got here? We've got a set of vectors, it looks like, where the vectors in this set are exactly the columns of the matrix A. That's where those columns A1, A2 up to AN come from. They're columns of your matrix A, which if statement A is to be believed, then it's an invertible matrix. So it turns out those columns are going to form a linearly independent set. Remember what that means? It means if you write any linear combination of the vectors in this set, the only way that can vanish or end up being evaluated to the zero vector is if all the weights or coefficients are equal to 0. Statement G says that the span of the columns of the matrix A is equal to something, and it turns out that's going to be equal to all of Rn. The language that you'll sometimes hear, sometimes books will phrase it like this: the columns of the matrix A span Rn. In other words, if you take their span, it turns into Rn. Remember what span means? It means take the set of all possible linear combinations of the vectors in your list. So the span of A1 through AN really means all the linear combinations you could ever possibly form with those vectors, and then put them together into a set. But this statement now is saying that that set is going to end up being equal to Rn, which means every n-dimensional vector can be written as a linear combination of these vectors. That's what you're really saying. Okay, that's the real essence of that statement, is that if you take linear combinations of the columns of A, you can obtain any n-dimensional vector in that fashion. Now that's not true for any set of vectors. That's a very powerful statement to make about a set of vectors, especially if there's n of them. The number of those vectors happens to be the same as the number of coordinates in each one of them. And you know that's true because A was a square matrix, by the way. Okay, so statement H. The linear transformation Rn to Rm defined by T of x equals Ax. There's a typo here, actually. Make this change. This M, and actually this one as well, should be an N. Because the matrix A is squared, or not squared, is square. It's got n rows and n columns. So this linear transformation is going to be a transformation that goes from Rn to Rn. In general, this is the number of rows of the matrix A. But if A has n rows, then it should be an n. And so same with this statement here. Okay, so what are we saying here with statement H? If you take the matrix A and you use it to define a linear transformation from Rn to Rn, you can always do that with any matrix. You can use it to define a linear transformation. It's going to be 1-to-1. Okay, that means if you take two different input vectors, you're guaranteed to get two different output vectors. Okay. By the way, this is abbreviated somehow. Sometimes this will be abbreviated in the following way. So I just want to mention that now and add this annotation. Sometimes you'll describe this transformation or this mapping or this function without, you might want to do it in the middle of a comment, right? You might be trying to just say something about this transformation, but you don't want to stop and say, okay, let T go from Rn to Rn, and it'll be defined by T of x is equal to A times x. Like maybe you just want to really quickly refer to this function in the middle of a sentence as you just kind of make a little bit of an inline comment. Then it's helpful to have this abbreviation. This whole thing can be abbreviated just by saying x is mapped to A times x, or x is sent to A times x. This is an abbreviation for this entire definition, okay? And the textbook uses this as well in places. So if you see this, it's really, you can expand it by just writing this. Now, sometimes this you'll have to just infer by context. The domain and codomain, that will have to be clear by context. But this is really just a short way of saying this. And notice the letter T didn't need to get written down here at all. And that's kind of one of the things that's nice about this notation, is it allows you to describe the actual action of the transformation without having to specify symbols to describe it. Okay, that's a bit of a digression, but you will see that notation sometimes. Statement I is almost the same thing, starts out identically, but you can say something else about that transformation. You can also say it's onto. And remember what that means? That means the codomain is also equal to the range. That means every vector in Rn appears as an output vector from this transformation T, if you can just find the appropriate input vector. So that's powerful information to make. By the way, so if A is invertible, that means both of these statements is true. That means your transformation T is not only one-to-one, it's also onto. So it's both of those statements are true. That's actually a very special type of linear transformation. A linear transformation that's both one-to-one and onto is called an isomorphism. Really, the essence of those kind of transformations is that they're preserving all of the algebraic structure from their codomain. And when they map it into their codomain, pardon me, I said that wrong. They're preserving all of the algebraic structure from the domain when they map it into the codomain, which is equivalently the range. Okay, don't worry about that too much right now. That's just a passing comment. Our last statement. Okay, A is a product of what? It's actually a product of elementary matrices. It might not be not necessarily just 2 elementary matrices. You might have to do it might be a product of, say, 30 elementary matrices. But there is a way to write A as a product. And actually, I'm going to, now that I'm thinking about it, I'm going to erase this word just so I can change the way this is expressed. A is a product. And just I want to write this to emphasize that it could be any number of factors. So I'm going to say E1, E2, all the way up to EK, where K could be anything, any large integer. So you have some elementary matrices, E1, E2, all the way up to EK, which when K might be large, where if you multiply all those elementary matrices, you get A back. So let's say it like that. Okay, so all those statements are equivalent. So that's a really a powerful theorem. And there's lots more statements that we could have added. And you'll actually, if you read the textbook for this section, you'll see there's a few other statements that we didn't include that we certainly could have. But by the time we get to the end of this course, this could easily double in length with more statements that can be added. So saying that a matrix is invertible, you're saying so much more than just that it simply has an inverse. Okay, so this reminder is just, I've already said this, but I really want, I can't say it enough times. This is hugely important. The power of a theorem like this is that if you want to check if any of these statements are true, you can check any of the other statements in the list instead. And same with checking that they're false. If one of these statements is true, they're all true. If one of these statements is false, they're all false. Okay, so what's next? So now we're going to talk about a definition called invertibility. And you might say, well, hey, we've already talked about invertibility. And that's true, but we've talked about invertibility of matrices, not invertibility of linear transformations. Now, it turns out that the two notions are very closely related, but nonetheless, they deserve to be introduced separately. So if you have a linear transformation T from Rn, oops, I covered up the last exponent, from Rn to Rn, we say that that transformation is invertible if the following is true. If there exists some other linear transformation from Rn to Rn, so we're calling it S, you can call it whatever you like, but just for the purpose of stating this definition, we need to call it something, right? So there's some other transformation, call it S, that admits the following two properties, actually. First of all, if we compose T with S in the following fashion. So I say, I take some input vector x from Rn, I plug it into S, and then whatever the result of that calculation is, so take x, plug it into S, whatever the output vector is, now I plug that into T. Well, the property is requiring that actually give you back the vector x that you started with. Okay, so the idea is you take a vector x, S maps it to something else in Rn, but then whatever that other vector is, T maps that one back to S, or back to X, pardon me. Okay, and then there's two conditions actually. That's one of the conditions. The other condition is that it works the other way as well. If I start by applying T to the same input vector x, they both of their domains is Rn. So it makes sense to plug that an n-dimensional vector x into either T or S. So I didn't leave myself enough space. Let me slide this over. So it turns out if I now take the result of that calculation, I plug x into T, whatever the output is, I plug that output into S. Well, that's got to also give me back the same vector I started with. And these two statements have to be true, not just for some vector x, but for every vector x in Rn. Okay, no matter what vector you plug in, both of these statements have got to be true. Now, if that's the case, then we say if there is such a transformation S, then we say that T is invertible. Okay, and then we can also say once you have it, you don't need to use the letter S anymore. Oops, you can just say T inverse. Okay, this mapping S, we actually give it a special notation in this case. We just say it's T inverse. So you can use the inverse notation on a matrix T, or pardon me, a transformation T, which you can also use it on. I lost my train of thought here. Let me start that sentence over. So you can use the inverse notation on a matrix, a square matrix, but you can also use it on a linear transformation T.